everyone. My name is Nafisa Mollai, and I am a postdoctoral research associate at Loyola University Chicago. My background is about how we can use AI algorithms in healthcare, especially in my postdoc research and working in large language models in healthcare, that how we can use these algorithms in our notes. So basically, we have overall, for example, progress notes or clinical notes in the physicians' notes. So basically, as you know, these kind of the notes are unstructured data, and our goal main is that how we can find a different kind of conceptual information from these kind of notes. So this information can be comorbidities, complaints, patient-reported adherence, and symptoms. So sometimes these kind of the points and these kind of the factors are hidden in the notes. So by using the large language model, we can find these kind of the, for example, comorbidities in our clinical notes. So basically, in our unstructured notes, we are looking for how we can use the NLP for a human language. So as you know, the human language is nonsense. So sometimes it's fuzzy, and sometimes it's contextual in information, and sometimes we don't know how we can interpret our, for example, sentences. I mean that, for example, in my conversation, we don't know if we are mentioned about the specific things that is in the news, or we are talking about the domain specific, that is, for example, just expert understand some kind of the expressions in our notes. So basically, by using this kind of complexity in our conversation, if we are looking for a new kind of the algorithms to find a better interpretation in our notes. So we can use the part of speech, spell checking, and we use some kind of ontologies, for example, by using BioBERT and clinical weight, and then using some machine learning and deep learning that these kind of tools can also use for our solution. And also in the notes, for example, the notes that I use, that there are notes from the physician who works on the inertia illness. So based on these notes, I can find different kind of symptoms, type of the pain, type of the different kind of, for example, body parts regions, and this kind of keywords can be extracted from our notes. So first of all, I wanted to describe about application of topic modeling. So topic modeling find hidden patterns between different kind of the words, and even we can find efficient exploration from the topic modeling. So we have to extract the conceptual information from the notes, and find a coherence between different kind of keywords, such as, for example, name entity recognition. And then by consult, and even by delivering our output to the physicians, we can find out how this kind of evaluation can be useful in clinical decision support. So by using this information, we actually design some kind of actually like a flow chart or trend for the physicians. So first we have a note, and then by using note we can find these kind of the topic modeling, and by using the topic modeling we find different topics in the our notes. So for example, we have topic 1 to topic M, and after that by using the classification we have a note 1 to note N, and these kind of the notes can be useful for the topic 1 to topic N. So we have different kind of progress notes based on each person, I mean that each person that visit the doctor. And by using these extraction of topics, we can find that how much these topics are involved, for example, in the progress notes. And after that, we are going to predict if these patients has the inertia or not. So here I explain about the different kind of the models. First, I'm going to talk about the LDA. LDA is one of the traditional model for topic modeling, but BioBERT and BERT topics that I bring here are I'm going to explain about them because I'm going to explain how these two are different from the latent and disjunct location. So first of all, LDA is, as I told you, is a traditional model. So by using the LDA, we can find how many words we have in the document and how many topics that related to those words are related to those documents. So by using LDA, we can find a different topic, for example, D1, T2, D3, D4, and each of these color showed different topics related to that document. And now I would like to talk about how we can work, how we can use large language models in inertia. So basically, large language models have a um, uh, potential useful algorithms for therapeutic inertia by extracting the clinical information from progress notes. And using these kind of large language models can be useful in detect inertia in hypertension management, and we can pre-processing these nodes to extract clinical information, and this clinical information can be input the pre-trained large language models to identify topics related to therapeutic inertia. So for example, one of these usefuls is that nowadays the patients call to the emergency department. So these conversations by the patients and the even operator is working to be automatically. So I mean that, for example, customer service that answer to the patients now is automatically by using large language models. And even, for example, some sort of boxes that return the identification of the patients are in their, for example, historical data. So basically, by using natural language processing, we can hidden the identification details of the patients in those, for example, data and those boxes that are related to patients because of the privacy. And I wanted to talk about the BioBERT. So BioBERT is one of the trends, large language models that recently working on that. So we have the progress notes here, and then by using the BERT, we can give them the weights to the different kind of keyword extraction, and then we use the pre-trained BioBERT. So these three pre-trained BioBERT in biomedical can be useful to extract this conceptual information. So fine-tuning of the BioBERT is one of the important part of these pre-processing. So actually, I use the pre-processing BioBERT to implement name entity recognition, relation extraction, and even question answering. So if I wanted to bring an example, we can see if the BioBERT shows OBI. For example, I shows that the failure is the beginning of the is the middle of the sentence, and B shows that this keyword is the beginning of the beginning of the sentence. And even with the relation extraction, we can find the relations between two different keywords. And even by using question answering, we can use the, for example, BioBERT to generate the text based on the our questions. And the second large language model that I implement in our algorithms is that BERT topic. So BERT topic modelings actually provide the automatically the searching and summarizing large electronics keywords, and then we can using from these algorithms to discovering the hidden themes in the collection and classifying the sentences into the discovered themes. And by annotating the document according to topics, we can predict the different kind of actually this concept information by optimizing the our search process. So first of all, we use the pre-processing. So we use the tokenizations to tokenize the sentences, and then use the lowercase, and then I use the contractions, and after that I remove special characters, and then I implemented limitations to extract the root of each word, and at the end I use the normalize and word embeddings for our pre-processing. So after that, I use the large language models. As you see, it's BERT topic. So BERT topic is one of the really recent large language models that is useful for the clinical actually clinical research. So this BERT topic shows that how we can integrate LDA and BERT. I mean that the vectors LDA and BERT, and how then we can concatenate and also using auto encoder for this latent feature, and after that how we can cluster our different topics based on our pre-processed database. Here I wanted to explain about what is the difference between the LDA and BERT topic and BioBERT. So BioBERT is really great in biomedical oncology, based on the understanding the clinical concept, and weaknesses is that there has many hyperparameters that we have to tune. But BERT topic is the easy to use, but it is a bit accurate from the BioBERT or LDA, and it's one of the great large language models that is useful because it's fast, but it is a bit accurate from the BioBERT and LDA. And LDA is more flexible, but it's difficult to use because there are many different kind of things that manually we have to tune them. So the result is that, for example, I use the progress notes for the progress note for the input of our algorithms. So for example, I had about this shows that the number of documents, it was around 500 documents, and the documents word account is around 1000. So as you see mean is 136, so around 125 word accounts in the around 495. So in our projects, we have 33,412, and there was about 6,757 about the patients, and the most visits are 35. So the patients who regularly visit the physicians is 35, and the less one is 1, and we have about 332 missing data. This missing data was related to, for example, demographic data. We don't have any notes for each visit, and the longest notes is around 32,607, and the shortest is 23 character, and the longest note is 5,132 words long. So the shortest character is also just 3 words long. So here I use I wanted to talk about the LDA that I already explained about that. It's about one of the traditional NLP, traditional topic modeling algorithms. So as you see, if we have a number of topics, for example, 250, and this trend shows that how the algorithms work by using UMass coherence. So UMass coherence evaluate the quality of topic modeling. So that's why I use the UMass coherence to show that how words appear together in a topic that should be semantically related, and how often, for example, two words would be expected to occur together by the chance. And this measure of the semantic coherence is one of the measurement of the topic modeling. So for the UMass, we have to trend as a minus. For example, as you see here is the points that we can count on, that these kind of the topics that we can use. For example, we can choose 56 topics that we gonna to understand how many, which kind of the topics there are. And for example, the next one is around 140. So these kind of the points are the points that we can count on them to consider them as our output to understand the topics related that. As I explained for you, here we have around 46, 48 topics. So in this figure is dynamic. So for example, here I choose my mouse in 2, so I choose topic 2. So here we have around 30 keywords here. So these 30 keywords shows that the red one shows how much these keywords are frequent in this topic, and how and the blue one shows that how much this keyword involved in all the documents that we have. So by using this kind of the illustration, we have to show these 30 keywords to the physicians, that they can understand, okay, if the patients in their notes have these kind of keywords together. So this patient, for example, has a diabetes. These kind of the evaluations are related to physicians that can give us the result of our output. And here is another kind of the visualizations from another method, which is named BERT topic. So BERT topic shows that how we can actually extract the topics related to each group. So we can manually choose how many topics we can have. For example, here I choose 10 topics. So among these 10 topics, we can shows that these kind of the topics that comes with each other, I mean that each group of topics are shown as a one disease, but because they have many, for example, expressions and comorbidities, we don't know. I mean that, for example, engineers couldn't interpret the BERT topic. So each group of topics we have to show to the physicians, that they can understand that it is kind of the topic, what is the name of each topic based on each group. So the score and the sort of each keyword are really important. And basically they can evaluate our topics around 1 or 2 days to give us the feedback. And here is another kind of the visualization for BERT topic. So as you see, we have two kind of the PCA in our method. So each of them we have 384 different topics from all of our progress notes. So basically each topic shows that inside of that topic, for example, we have another topic, but overall, if I can interpret this figure, I can say that the topics that doesn't has any another topics inside is better, and even these kind of topics should be separately. So it is better that each for example, circle are very far away from each other, and there is no other topic inside it. For example, is one of the, for example, words topics, that because the keywords covers to each other. But for example, I can say these topics are a bit better, but for example, this one is because very far away from other topics and is alone, it is better topic for understanding the and predicting the disease. So here is for example, one of the topics that I extracted from the clustering from the BERT topic. So as you see, by using the hierarchical clustering, we can understand which kind of the topics comes to each other. So these kind of the models are automatically determined by the BERT topic. So for example, as you remember in previous slide, I told you that we choose 10 topics manually, and for example, for each group we choose 10 from 10 keywords. But here for the clustering, we give all the information to the for example, algorithms, and algorithms itself choose, for example, we have to around 9 topics, and and each topic should be 5 keywords, and it can be showed by the different kind of the color, and this kind of the color can be for example, I just bring an example for my progress, which is 33,000 progress notes. It shows about 50 different color like this to show different topics automatically. And here it shows that another kind of the visualization that shows which kind of the topics are more trend in um, overall our evaluation. For example, topics are represented by the number of the words starting with the best representative word, and each word is represented by a classification TF-IDF score, and the higher score is more representative a word to the topic is. So for example, the first one that you are seeing in the figure, so this figure shows that a classification TF-IDF score, so log scale and term rank. So it shows that, for example, in each in overall our iteration, which kind of the topics are more trend. So for example, or among 384 topics that we have, for example, topic 4 are more trained in our overall progress note. But as you see, for example, RMF would be one of the expressions in the progress note full detect and duplicate. So these topics with these keywords are more trending overall progress note. And the second one that, as you see, it shows that the topic 69. So topic 69 with case attend, residence, agree, internal is another topic that is shows more that is shows in overall in our progress notes. So as you see, these kind of the visuals are really nice for the physicians, and physicians give me feedback that we can understand that, for example, the status of the patients, and from that period, for example, December 2029 to 2023, we can understand these topics are more trend, and these kind of the problems are more they're duplicated in the progress notes. So thank you very much.